Can you hear me through the mic? Yeah. I'm going to try to stay with this recording for a while. And you guys can access these recordings on Canvas on the site. So if you're interested in doing it that way, it might be useful. I'll wait another minute for the strict top of the hour. Okay. It is my experience that if you understand the things you have studied thus far, you understand the things you have studied just thus far, 21D is a much easier experience than if you don't understand them. Now, people sometimes think they understand them, and they don't. They sort of kind of get by. Okay? There's a very significant difference between getting by and understanding. And I am doing this review of ideas from 21B and 21A right now because I want you to understand what they mean, because they will contextualize our learning for this class. Okay? That's really what I'm trying to do. And the first thing I've talked about, and I want to recap it, is the integral of a function f of x over an interval. X is in a to b. That's all that thing means. So x goes from a to b, some number 5 to 7. Okay? It is written as that. That is a shorthand. That is the way we write the sentence that is above it in mathematics terms. If I were to simply write that sentence, that object, and you were a high schooler, it would have no meaning. It would have no meaning whatsoever, of course, right? We have to give it meaning by defining what we mean by the integral. And that's what was the subject of 21B. We spent time defining what we mean by the integral. And so we defined that sentence, which we shorthanded with those symbols. We defined those things in the following way. And I talked about the different definition last time. It is this Riemann sum definition that you understand, okay? So I have written the definition down as we had last time, and I have a little diagram there because this, of course, has no meaning unless each of its parts are defined, okay? And you can go really philosophical and go turtles all the way down, okay? But it's not, okay? You know, addition is something you have to define, right? You define it when you're like, you know, a year old. 1 block, 2 block, 2 block. I want more. More is good, okay? Now, we don't necessarily think that way about mathematics. We think that everything is just presented to us. It's all the same, okay? But that's the way you need to think about what you're learning in this class right now. That's why I'm trying to tease apart these three notions. In fact, there will be 4 notions, okay? The 4 notions that I'm trying to tease apart are definition. What is a definition? Theorem. What do I mean by a theorem? Proof. What is a proof? And then this idea of metaphor. What do because we use metaphors to understand these definitions or these theorems. I am doing this because I have asked on quizzes and tests in the past, I have asked, can you tell me the fundamental theorem of calculus? And people would say, or no, can you tell me what a theorem is? I would say, can you tell me what a theorem is? A theorem is a definition and a proof. I was like, ugh. Or what is a proof? A proof is a theorem. They use like theorem and proof and definition because they've all been you've seen them in those boxes, right? On calculus textbooks, you've seen them in those boxes. And you're like, oh, they're sort of all in a box. So they must have something, they must be the same, okay? So, I don't want to get too philosophical here, but I kind of threw this out at you last time. A definition, we get to make definitions. We start off with definitions. We define a thing that we are going to play with. That's what mathematics is, play, right? So we define a thing we're going to play with. A definition is like the building block. And I love my Lego metaphor, so I don't know if you like my Lego metaphor, but it's my building block, okay? And so here's my I'm going to try to make a Lego block. My drawing will get better when I'm less in haste. And there's 1, 2, 3, 1, 2, 3. It's a 3 by 2 thick block, colored, transparent, apparently. Okay? So that's a definition. Building block. Theorem. How do the building blocks, how the building blocks connect and make something bigger? So this is like a statement. Okay, that's just the statement. So I would say this is, my, now you're going to really laugh at my drawing. If it's anything more than a stick figure, I'm toast, right? So here we go, la, la, la. Here's my space Legos from when I was a kid. I don't know, a spaceship. This is a spaceship. It's not a spaceship. It's terrible. But that's a spaceship, okay? It's made up of a whole bunch of these Lego blocks, okay? And I'm going to tell you, I can make a spaceship. Okay? That's what a theorem is. Proof is the instructions to connect the blocks. Okay? Now, people, if you wanted to get into the philosophy of this, there's a whole philosophy of this, and mathematics loves philosophy, and we could get into the philosophy of that, but I would like you not to get too deep into this, but just to sort of see the world in this way, okay? And maybe use this to contextualize what you're about to learn in this class, okay? And I'm doing this because then there's this other thing called metaphor, right? When I'm building my spaceship with Legos, have I really built a spaceship? Right? I call it a spaceship. But it's a little object that I kind of think a spaceship should look like. So, metaphor. A metaphor, in this sense, in the sense of mathematics, the way I want you to think about it is a simple relationship between a new idea and something you understood already. Okay? And I'm telling you, there's a reason why I'm doing this right now. Okay. Okay. Now let's go to a specific connection here. The integral of a function over an interval is written as this. It is defined as this. The derivative of a function is written, written as df dx, which is a function of x. So that if I have a function f, its derivative is written as df dx. What is the definition of the derivative? Does somebody want to chime in with that? The derivative is defined as, yes? Okay, so you are getting into the world of metaphor. What is the definition? There's a concrete definition. The slope at a point. The problem with slope at a point is that there was that subtle little thing that we had to do to connect the point, to get to the point, right? Slope of what? Slope of a function? It's not actually the slope of a function, right? We created those secants. We created a whole bunch of secants. We fixed one point, and then we shot lines out to another point. Remember that? So we had like a function over here, and we did this, and we fixed a point, and then we fixed another point. We said, hey, just draw a line right there. Right? That's how much this line sort of corresponds to how much change there is from this point to this point. And like, let's fix this point. Let's call this point x star, our special point. We're going to fix it there, okay? And then we're going to move this point closer, and I'm going to go shooting over there. And then I'm going to go shooting over there, and I'm going to go shooting over there, right? And so I know you have a sense of what you were saying, right? But I want you to be really precise about it and say, oh, look, there's these secants, and in the limit that this distant point approaches the near point, I can consider the slopes of each of those secants in that limit also. And the slopes of those secants, if the limit exists, we call that the derivative. Right? That's a lot of words, right? It's a lot of words. But we have a very simple definition of this object. Somebody want to tell me what the definition is algebraically? Sir? That's the definition of the derivative. That's the definition, okay? That's the definition. And if any of you guys took my 21B class last year, the derivative is subtraction and division with a limit. With a limit, okay? Kind of, that's our hidden secret. Subtraction and division, whereas the integral is multiplication and addition. Okay? Multiplication and addition are inverse operations of subtraction and division. So it's not too freaky that these two operations, the derivative and the integral, are actually inverse operations of one another. Right? It's not too freaky. The issue is the limit, because I've tucked that limit in there and I don't want to talk about it, right? Okay? But it turns out that they are, and there's a theorem. There's a theorem, theorem, which is the fundamental, well, you know it's important. Theorem, you know it's a theorem of calculus, you know you're in the right class. Calculus, okay? And the fundamental theorem of calculus says the following thing. Now I need to start using shorthands, because I don't want to write this all the time, okay? And I don't want to write this all the time. So then I go to the shorthand, which is this and that. And the shorthand says, if you take the integral of a function from one point to another, but that function is the derivative of another function, the integral of the derivative is equal to, and this is a function of x, so I'm going to write this, by the way, explicitly as a function of x. That's equal to the function f evaluated at the upper bound of integration minus that same function evaluated at the lower bound of integration. That's what you guys built up for 2 quarters of calc, right? That's what you figured out. I know it's total review, and I hope it's not too boring, but I really want to tease out this idea, okay? By the way, there's another statement of this theorem, so that's one way to look at it. Another way to look at it is the following. If I take a function and integrate it, so let me say integrate it from a to a general point, a point x. So I'm going to make x variable, okay? And I'm going to take the integral of that function, f, with respect to something. So f has an argument, right? Now, I'm a big opponent of indefinite integrals. I hate indefinite integrals. I like definite integrals. They make me know like what I'm doing, okay? And so I insist that you cannot use the variable x in here. Because just as the variable, this index I does not survive the summation, nor does this variable in here survive the integration. We have a name for that. We call that a dummy variable. It's a dummy variable. I think you've learned the word dummy variable before, right? And so I often use x prime. Is that okay? It's not the derivative of x. I saw a face. I've taken I've been doing this for so long, I'm sort of flexible with the notation. So you didn't like x prime. Which one do you like? What do you like for a dummy variable? Woman with the glasses in the middle. Yes. What would you use for a dummy variable in this case?
Just for handwriting, say
t. Let's use t. Okay, for handwriting's sake, let us use t. I like it because it's one thing, and you can't tell the difference between a little prime and all the other mess I write on the board, right? So f of t dt, okay? And if I were to take the derivative of this with respect, now can I take the derivative with respect to t? Makes no sense, because t has been integrated out of the problem. But I can take the derivative with respect to the things that remain in the problem, a or x. And we commonly take the derivative with respect to x. And the derivative of this with respect to x is what? By the fundamental theorem of calculus. Pardon me. What is it by the fundamental theorem of calculus? Yes. It's f of x. This is the statement of the fundamental theorem of calculus. That is the statement of the fundamental theorem of calculus. They're both statements of the fundamental theorem of calculus. The first one says integration, then differentiation gives you function. The second one says, the first one says, oops, misspoke. This one says do the derivative first, and then integrate. And that returns to you the function with some combination. This one says do the integration first, and then differentiate. And that returns to you the function. A simpler combination. Those are the two statements of the fundamental theorem of calculus. They are a theorem. There's a theorem there. So proof. 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 Well, as you know, proofs take a bit of time. And I'm not going to do the proof for you right here because you did it in 21b, I hope. Right? But there is a proof. There is a way to prove these two statements, okay? And what do you need for the proof? What you need to prove something is you need the definition of the derivative and the definition of the integral, and you need some ingenuity to try to connect them. That's all that you're doing. So when you say, I need to prove that the derivative and the integral are opposites of one another, you say, I go to the definition of each of those ideas. And from there, you can make the connections, okay? Now, of course, I'm not going to ask you to prove ab nihilo from nothing, right? I'm not going to ask you to memorize necessarily a lot of proofs. That's not what I want. But I want you to sort of have a sense of how this process is done, okay? Okay. Now, this is a hard class to ask questions of. You guys are not, I mean, it's just a big class, and I ask questions, and I get those long silences. So I do this whole thing because in this class, my objective is to generalize the definition of the integral. We're going to make it bigger. We're going to learn more about integration. And then I'm also going to generalize the notion of the derivative. We're going to make it bigger, okay? And then I'm going to connect those generalized ideas, okay? That's what we're doing. So if you don't know the basic ideas, to create the generalized ideas is going to be terrible. Okay. And the reason I write this board over here, definition, theorem, proof, and metaphor, is because I have asked in the past, and maybe you guys are not the same, I've asked in the past, what is the integral of a function over domain A to B? So what is the integral? And who might answer that question? It's the area under the curve. Who might answer that question that way? Come on, just admit it. I'm going to tell you you're wrong, but just admit it. Be proud. Be proud to be wrong, okay? It's the area under the curve is what we're taught, right? We're taught area under the curve. I learned that in high school calc, right? And area under the curve. But of course, you have to contort yourself in all sorts of weird ways when the curve goes below the axis. And then you say, well, it's the area of the curve to the axis, and then you have to account for negative area down bottom. And then you're like, oh, yeah. And then you're going to realize in 21D, we're going to really talk about area, really area. And you realize that, my dad, my dad worked in construction, and, and I helped him out. And if I were to go up to him and say, Dad, I got negative 5 square feet of tile I need. Dad would go, whack, right? Are you kidding me? Well, I didn't bring up my son to say that, okay? Because area is a positive number. Area is a positive number. Area is something that we measure, and that is true. And you know that because you've known that all your life, right? You know you need a surface area of a room. You go rent your surface area of the room, 100 square feet nowadays, pays $1 million, right? So I want you to not think of this metaphor, area under a curve, I'm trying to unteach you this metaphor. Unlearn this metaphor, okay? Or at least be careful with it, okay? If you're not willing to unlearn it, just be careful with it. Because when we get into multiple dimensions, it is not generalized well, okay? Here's a perfect example. Area is measured in square meters, or square feet, okay? Area is measured in square length. But many functions we have units of, say, temperature or density, some physical quantity. And so when you talk about the area, okay, I want to show you, right? Now, this is a moment of discussion of units, because you guys are engineers and you're going to be measuring things, and you've got to be building bridges, and they better be made in the right units, because you remember some Mars rover many years ago was using the wrong units and smashed into Mars. So let's imagine X is measured in meters, and F is measured in potatoes, okay? Potatoes. And I really mean anything, right? Anything you want. Kelvin, grams, I don't know, whatever it is. What is the unit of the number that you get when you perform this calculation? But what? I can't hear you. Yeah, and it is. It is, say it loud and proud. Potato meters. Potato meter. Potatometers. Okay? It is potatoes times meters. Okay? And this is something you don't get out of calc in math books. Okay? But you must put in your mind if you're going to go to a physics class, or you must put in your mind if you're going to go to an engineering class or any science class. Integrals have units. Derivatives have units. Because integrals are multiplication and addition, right? They have the units of the things that you are multiplying. Because derivatives are subtraction and division, they have the units of the things you are multiplying. I cannot overemphasize how important it is to carry your units, at least in your mind or in your pocket. So when you check if you get some weird calculation, you check it. You're like, what was the unit there? Oh, I got potato meters. Nobody wants to know what potato meters are. I multiplied the wrong thing. Okay? So I emphasize this. And so I'm going to put a different metaphor in your mind, and it was there in Calc 2 for you. Okay? And the metaphor I'd like to have in your mind, or the metaphor, the interpretation of the integral comes from this observation right here. Well, it comes from this observation. Okay? Step 1. I can integrate the function from a to b of the number 1 dx. What are the units of the number 1? It is simply the number 1. That is to say, in the definition, f, I reproduce with the number 1, pure 1, 1. Nothing there, right? So what does this create? Well, and I'm going to keep x in meters. What does this create for me? Well, this creates the antiderivative of the number 1, which is x evaluated b minus a, which is b minus a. Okay? And what this produces is the length of the interval. This is the length of the interval from b to a. So it's a very complicated way to get the length of the interval from b to a. What does it tell you to do? To calculate the length of the interval from b to a, you plot the function 1, which is a constant, has no units, 1 with no units, and you go from b to a, from a to b, b to a to b, okay? And you take that thing and you chop it into little pieces, and you measure each of the little pieces, and then you add them up, which is not a very complicated way to measure the length of that. And then 2, the second thing I want to show you is this function here. Imagine a very simple function which is positive. Let me say this is 5 grams up here, up till the number 1, and then it's negative up till the number 2. This is 2 meters, maybe 5 grams. No, 5 coulombs. 5 coulombs. Coulombs. We know what a coulomb is, okay? Because I better not have negative grams. That's ridiculous. Already I've given you something ridiculous. But let's say 5 coulombs, which is the amount of charge. And we know we can have negative coulombs. This is negative 5 coulombs. And maybe this is the amount of charge, some sort of charge thing on an interval, some sort of wire. What is the total charge on that wire? What's the total charge? Well, you got to integrate. You got all these 5 coulombs. You got positive over here, and you got negative over here. And if you just say, what's the average of this function? You can see if this is negative 5 from 1 to 2, and this is positive 5 from 1 to 2, the average, if it wasn't coulombs, I just threw that out, but it could be anything. The average value of the function is 0. The average value of this function, as I've written it, it's a stepwise constant function. Its average value is 0. Okay? Piecing it together, it'll come together. I swear, it'll come together. I hope I'm not too, I know I'm a little slow today, but. And if you were to take the integral of this function, you would get the number 0. Because the way we learn the integral, it's the positive number times the area under this curve, and plus the negative number times the area between here and here, so it's a negative, they cancel out and you get 0, okay? So I think the better metaphor or way of thinking of the integral for the integral is that I'm going to tell you it, I'm going to show it to you. The integral from a to b of f of x dx is the numerator of the average. It's the numerator. What do I want to really say here? Let's imagine a function. Consider f of x, and the interval x is in a to b. Okay, so 5 to 7, whatever, put your favorite function over there. And I want to measure the average value of that function. Okay? If the function has units Kelvin, let's do Kelvin now. Okay, so we're going to imagine a wire, and the F is going to be the temperature in Kelvin. Okay? What is the average temperature measured in? If the temperature is measured in Kelvin, what is the average temperature measured in? It better be measured in Kelvin. It has to have the same units. Okay? So if I calculate this, the integral from a to b of f of x dx, we know that that thing has units Kelvin meters. Okay? That's not Kelvin. But if I were to divide this by this, the integral from a to b of the number 1 times dx, this has units meters, this has units Kelvin meter. Kelvin meter divided by meter, this has units Kelvin. In fact, this is what we mean by the average of a function. Okay? Now, how could I prove that to you? Well, I would prove that, and you guys did this in 21b. Okay? You did this in 21b. How do you prove that? Well, you start off with a constant function, and you realize that the average of a constant should be the constant, and that it works out just right. And then you do a linear function. Okay? And then you think, well, the average of the linear function should be the midpoint in height. Right? And you work it out, and it works out just right. And then you realize, okay, from there, every function can be approximated very locally by piecewise linear pieces. Right? That's what we do. That's what the calculus thing is. You zoom in, everything, it looks sort of straight. if it's small, if you have a small enough subinterval. And then when you generalize from there, you'll see that this all works out. I'm not going to work it out for you. But this is the metaphor you should have in mind. That is to say that the integral of a function from a to b is the average of the function on that interval multiplied by the length of the interval. That's all it is. That's what we mean. That's what the integral is useful for. And now it makes sense when you have functions that go negative, right? Because if they have the same amount positive and the same amount negative, their average should be 0. And that'll work out. And that's the metaphor you have in mind. OK? If you understand all of that, chapter 15 is easy. Chapter 15 is the chapter we're doing in the book on multiple integrals. Integrals in 2 dimensions, integrals in 3 dimensions, coordinate systems, and transformations between those. How to do and generalize the notion of the integral. OK? So I talked a lot, and I see all these faces. You're still looking at me. Not everybody's asleep. That's nice. I'm sorry, I'm long-winded. 30 minutes to listen to me is a lot. So break here and say, ask me a question. Is there anything that I've left out? Is this too obvious for everyone? Maybe it's very obvious to you, but I kind of wanted to go. It's just September, right? I mean, we're dusting off the cobwebs of summer. So, OK, yes? Well, x. It is very, you're right. Where am I getting the meters part from? I just said meters. Whatever the independent variable is. I'm a physicist, and I kind of think in 2 very common independent variables. I think of functions of location or functions of time, right? And those are very common independent variables. We could get more general than that, OK? We could get very general, but it doesn't matter. Right? It is whatever your horizontal axis is, it has units. And because of the way the integral is defined, that unit gets thrown into the computation of the integral. OK? That's it. OK, chapter 15. The double integral. So, chapter 15 is integration in multiple dimensions. OK? Multiple dimensions. I'm sorry about my terrible handwriting. I speak it out, so the hope is you're writing it as I'm saying it. Section 15.1. I think it's called the double integral, but I don't want to think about a double integral. Integrals over R2. Integrals over R2. OK? R2. So this is, and I went into that kick about area because I really want to, because I've seen confusions happen in this particular section, in the first section, because of people holding on to the metaphor of area from Calc 2. OK? So the first thing we need to realize is that we had functions of 1 variable, f of x. Now we are going to consider functions of 2 variables. So consider 2 independent variables, x and y, OK? And this is an ordered pair, and they are in, this just means in R2. And all this R2 means 2 real numbers. One real number tells you this, the other real number tells you that. And to each of those 2 real numbers, at each pair of real numbers we assign a number, another number, f of x, y. Okay? In this section, I like to use the concrete example in your mind of temperature as a function of where you are. Okay? X and y tells you where you are. Okay, we're all at the same z. Let's pretend. Okay? We're all at the same z. It's warmer over here because of the electrical equipment. It's cooler over there because the door is open. I don't know. Right? It's a function of where I walk in this classroom. Okay? Now, the first question I have for you is how do we visualize functions over R2? And there are two ways to do this. There are two ways we learned how to do this. Okay? One way is because we can draw R2 at least in perspective. So because we can draw 3 dimensions, at least with some sort of perspective, better people than me can do it, right? We imagine way number 1 is you create an axis, x, y, and then you have a third axis. Okay? That third axis is not z. I don't want you to really think of it as z. Okay? It is because, again, these guys might have units meters and meters, and this is not going to have units meters. I think of x, y, z as sort of flowing continuously into one another. If it's meter, meter, meter. It's going to be the value of f of x and y. And so what you do to represent this function graphically is you go to a point. So you take the x value and the y value. This is the point in the independent variables. This is R2 down here. This plane, okay, is R2. And I take the value x, maybe say I call this 5 and 2. And so this is the point 5, 2. So I've chosen 2 particular values. And then I have a value of the function at 5, 2 because the problem has given it to me. And so there's a point. I got to, the failure of my drawing. There's a point, right? And you got to kind of get a nice perspective here. And this is maybe 7 Kelvin, okay? 7 Kelvin. So this is 5 meters from an agreed upon origin, and then 2 meters from another agreed upon origin, and it's really cold over there. 7 Kelvin, okay? 7 centigrade. Let's maybe call it 7 degrees Celsius. 7 degrees Celsius, okay? It's still pretty cold. Okay, and then you do that for all the points, and you realize that you create all of these points everywhere. You create all of these points, and those points actually create a geometric shape. If you were to, by the way, these curves will be coming up a lot when we do integration on curves, which we will be doing. Okay, and so if you move this point, go 5, 6, 7, 8, and then you have this whole slice over here. And then you got another slice over here if you've moved from 2 to 3. And you got another slice over there. And this is where colored chalk would really work. So all those curly points, so the curly curves, right, they are supposed to look like a surface. That's supposed to be a surface. And so one representation is a surface plot. Surface plot. Okay? Now, computers do that. We have algorithms to do that. People developed these algorithms in the 60s and 70s to actually create MATLAB that did all these awesome quick plots, right? So we know how to do that. Okay? A second way to represent functions is isocontours, isolevels. Isolevels, or in 2D, isosurfaces. Contour plots is another way for it, a contour plot. And the contour plot, I like it because it avoids the problems with trying to draw things in perspective and draw things over one another with a perspective, and I'm a terrible artist. And so what you do in a contour plot is you just draw the x and y axis, okay? And then you choose a number, a value of your function. In this case, let's choose 7 degrees Celsius. So I would choose, e.g., choose 7 degrees Celsius equals f of x and y. You set the function equal to a particular choice. Okay? Now, you've chosen 7 degrees Celsius equals f of x and y. Now, that is one relationship on 2 unknowns, right? F of x and y is equal to 7. Okay? That's one relationship. One equation is one relationship between these 2 unknowns, x and y. Okay? And so that gives you you go from a two-dimensional space, when you have one relationship on two unknowns, you drop a dimension and you create a one-dimensional object, which is a curve. Okay? So the example, here's a very simple example to make this concrete. Okay, I'm going to do this. E.g., let f of x and y equal 5 Kelvin. I'm going to keep units here because I know just to cause you grief. You can hate me for it, but you'll like me for it later on. Multiplied by the square root of x squared plus y squared over let me do it this way. 35 Kelvin, call that 35 Kelvin, times the square root of x squared plus y squared over 5 meters. You can see I'm totally making it up as I go along. Okay? Yes? Yeah, of course, it was Celsius. I went from Kelvin to Celsius. Yes, Celsius. Make it Celsius. I'm just trying to put a unit in there, right? But thank you. It's Celsius, everybody. Thank you very much. So 35 Celsius, okay? And so what are the units of F? What are the units of F? Well, x and y are lengths, so these have units meters squared, square root. This is meters, and I put in a constant of the problem, 5 meters. That is something given to you by the problem, right? You never see the units in math books, but you will be seeing the units in your physics books all the time, okay? So I'm kind of trying to introduce that to you too. And so this is meters divided by meters. This whole thing is unitless. Meter divided by meter is unitless. And so this is in degrees centigrade. That's awesome. Now, how do I draw the contour for this? Well, one contour is given by that process, okay? So let me draw the 7 degrees Celsius contour by letting 7 degrees Celsius equal f of x and y. And now you know why I was fuddling around with the numbers, because I wanted them to work out nice. So I write 7 degrees Celsius is equal to 35 degrees Celsius times the square root of x squared plus y squared over 5 meters. Okay? So you can see that I multiply by 5 meters here, and I'm left with 35 degrees Celsius meters is equal to 35 degrees Celsius times the square root of x squared plus y squared. Okay? And of course, I can divide by 35 degrees Celsius on both sides. And if I divide by 35 degrees Celsius on both sides, I'm left with 1 meter, which is the left-hand side. 1 meter is equal to the square root of x squared plus y squared, which may not help me very much yet, because I got a square root in there. So I'm going to square both sides, and I'm left with x squared plus y squared is equal to 1 meter quantity squared. And then I look here, and my toolbox of all those bajillion problems they made me do all my life, and I recognize that x squared plus y squared is constant, is the equation for a circle. Okay? This is the equation for a circle of radius this. And now by keeping units, I see explicitly it's a 1 meter circle. It's 1 meter. It's a real measurable circle. Okay? So if I draw that contour, now by the way, this contour totally does not correspond to this function. Okay? It's a different thing. Okay? So don't think I'm trying to represent that surface plot. And now I draw a circle of 1 meter. Okay? This is 1 meter. So this is 1 meter, this is 1 meter, this is negative 1 meter, which means go left 1 meter. This means go right 1 meter, go forward or go backward 1 meter. That's x, that's y. Along this circle, the temperature is 7 degrees. I've just drawn one contour. Whew. Right? I got to do a whole bunch of them. I got to keep going. A computer can do that. Right? But you're like, oh, look, if I keep doing this, I can see how this is going to go. Okay? And you can see that the temperature is increasing, in fact, linearly with distance away from the origin. At the origin, right, we can go back and show that the temperature there is 0 degrees Celsius. So the water is frozen over there, and it keeps getting warmer and warmer and warmer, linearly with distance. In fact, that square root function right there is the distance function to the origin. It tells you how far are you from the origin. If the origin is at 0, 0, and you are at xy, that's how you calculate it. Okay? So these are the two representations. Now we got to do some calc. Okay? So who's seen contour plots before? Everybody's seen contour plots. Be honest with me. This is totally fine. Was this review at all helpful? Yes? Okay. I do really like to go through these fundamentals a little bit because I feel like people have a tenuous grasp of them, okay? And it's okay if you say no. I mean, I'm always trying to change the way I present things, so I'm trying to do better next time. Not for you, though. You're stuck with me right now. Okay. Well, now I hope to tell you, right? I hope you see at this moment that the definition of the integral over 2 dimensions is ridiculously easy, right? Because go back and do what you did in 1 dimension and now do it for 2 dimensions, okay? Put all the pieces together, okay? So, consider, okay, we are going to define, we are going to define the integral of a function f of xy over a domain. I'm going to call the domain D, and it's contained in R2, okay? A domain D contained in R2. And the way we do it is as follows. We draw an xy axis, and before we had an interval, we went from A to B. We went from a start to a finish. But here now, we're in 2 dimensions, right? In 1 dimension, the natural thing was an interval. In 2 dimensions, the natural thing is areas. Okay? The natural thing is areas. So I'm going to imagine a room or a pool, okay? A jelly bean. This is my what I call the canonical jelly bean domain. Because I want it to look kind of general. Okay? That is the domain. That is not a contour of a function. So say it to yourselves, not a contour of a function. Maybe write it there. Not a contour of a function. This is the boundary of D. D is the inside of this stuff. D is the inside. Okay? And now I have this other, so that's the domain. Okay? You could have imagined that it's just a room of that shape, or a pool. And now I have some function. I also have f of x and y. And here, please do not confuse this. I might have a contour plot of the function. Okay, maybe the contour plot is the one that I just did a moment ago. These concentric circles all centered on the origin. Okay? There's the contour plot of the function. Contours of f of x, y. Okay? And so what do we do if we want to consider the integral of f of x, y over this domain? We do exactly what we did when we did in 1 dimension. Okay? What we did in 1 dimension is we took this domain, we took our interval, but in this case it's the jelly bean domain, and we chop it up. Chop, 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 chop it any way you want. Okay? And this is actually kind of crucial to understanding this, is that you can chop it how you like. You can have it your way. Okay? And so I'm going to label each of these. I'm going to label each of these by a number. This is going to be I equals 1. I'm going to start here. 2, 3. This is number 2, number 3, number 4, number 5, number 6, number 7. You can chop them up any way you want. Okay? And in each of these subdomains, I'm going to put a point. And I'm going to put a point here. And I'm going to put a point here. And I'm going to put a point here. I'm going to put a point here. Okay? This point here, okay, this is going to be xi, yi. That's the locations of that point. That's the generalization of the ci, right, from the one-dimensional integral. So it's some point inside this subdomain. And then what I'm also going to do is I'm going to measure the areas of these subdomains, okay? So here, I'm going to zoom in. So let me zoom out, or zoom in, sorry. Zoom in to that piece right there. Okay, that's this piece right here. Okay, so let me put a little asterisk there because I'm zooming to this thing. I mean, that's not much of a zoom, is it? That's a pretty bad zoom. Bad magnifying glass. Bigger zoom. Okay, that's that piece over here, that special one. I put a little star there to say, hey, that's that special piece. Okay, and I'm going to measure the area of this piece. Okay, somehow. Let me say that this has delta area is equal to delta AI. Now you have all the pieces to define the integral of the function. I'm going to write it. The integral, and then we write it with a double integral because it emphasizes that we are in 2 dimensions. Okay, and it's going to be called the double integral, but after we do another theorem to show that it's a double integral, because it's actually 2 actions we're doing. But really right here, all you're doing is say, this is the shorthand, the double integral of f of xy over the domain D. Notice I'm not writing an interval a to b because it's very general right here. Integrated with respect to the area element. So this is the double integral of the function f of xy over the domain D with respect to a, the area element, is equal to the limit as the partition size goes to 0 of the sum I equals 1 to n, we'll do capital N because I think I did that last time, f of xi, yi, delta ai, where P is the choice of chops, of cutting, that's the partition. It's the partition. And the magnitude of P is equal to the biggest area, biggest delta AI. So P is a set. This is a P, which is how you've chopped it. Okay, I give you all the same domain, and you all chop it differently. You all have different P's. You go measure all of your areas of those chops,